The following video is an unsophisticated essay of physics. It is not peer-reviewed and should not be cited as a truthful source. The goal of this video is to bring forth speculative ideas that have not been fully explored. The ideas of part 1 are somewhat needed to understand the subject in this video. The current known physical cause which explains why we cannot go faster than the speed of light is that the faster you go, the more your passage through time is slowed. When your speed converges to the speed of light, the time you experience converges to 0% the normal time you would encounter on Earth. In the first part of this trilogy, I presented an explanation that could instead link normal electromagnetic interactions to this time dilation. If it would be somewhat true, what else would explain our inability to move faster than light? In a mathematical point of view, reaching such velocity requires more and more energy. In fact, the increase of energy required to accelerate any mass near the speed of light is proportional to the Lorentz factor. In my prior video called The Emergence of Kinetic Energy, we have seen that indeed a particle with rest energy E equals mc squared will have its energy increased by the Lorentz factor depending on its speed. In a normal situation, kinetic energy is simply equal to mv squared divided by 2. Let's take an arbitrary amount of energy that is transferred into an object as kinetic energy. Why would the added velocity converge to 0 when the initial velocity of the object is close to the speed of light? One intuitive but naive answer would be that the closer it is to light's speed, the less it can be pushed from behind. Let's take two protons fired at tremendous speed. The one behind emanates electromagnetic waves much slower into its neighbor than the other way around. The proton in front therefore receives much less energy from behind. If they were actually moving at the speed of light, the slower electromagnetic waves could never reach the other proton. The reason why this answer is naive is because this would not apply to attractive forces. If the particle in front would be an electron, the attractive electromagnetic waves will reach with even more intensity than usual, which would intuitively enable the proton to breach the speed of light. A quite repulsive theory, pun intended, to explain the barrier of the speed of light would be to postulate that all fundamental forces are in fact repulsive. This is truly blasphemous considering what we know and all that we can see with our own eyes. Yet in this video, I will try to explore this idea and show why it is not as far-fetched as it might initially seem. I will try to use already known postulations as much as possible instead of blatantly suggesting the existence of unknown or unseen dimensions or particles. Let's begin with electromagnetism and its main attractive effects. At first, I will look over the microscopic attraction of protons and electrons. Usually, the postulation of negative and positive charges is the classical explanation of why these particles would stay close to one another. Because there is no need to distinguish repulsive and attractive forces of electromagnetism, I will ignore the postulation of charges. By doing so, protons and electrons should repel one another. The first consequence of such a thought would be that electrons would be repelled far away from protons. In a point of view of a couple of atoms, that would indeed be the case. Yet, in usual circumstances, protons are far too abundant for the electrons to escape. I will compare the repulsion of 3 close protons unto a lone electron versus the repulsion of all other protons in a very large radius. The violet surface of the example will be a stable area, and the orange surface will be unstable. Initially, the 3 close protons create an unstable area for the electron. It might get stuck between the 3, but eventually it will leave when it finds something better. However, if we look over at the electromagnetism of all other protons, the 3 close ones will easily absorb this chaotic background with their enormous mass. If we include all protons, there will be a small area where the electron will be somewhat stable between the repulsion of the closest proton and the lack of repulsion from protons behind it. Indeed, the electron will be pushed by both the closest proton and nearly all other protons behind it. This area can be known as the orbital. In past classical theories, the orbitals cannot be maintained using attractive forces because the electrons would, at some point, fall into the proton as its attraction should increase as it comes closer and closer. In terms of microscopic electromagnetism, there are other consequences in play, such as the formation of molecules, but they will use the same logic. There will be a little bit more on the subject at the end of this video. The effects of attractive electromagnetism can also be seen by macroscopic effects. The most known ones are attraction through magnets and attraction through electric currents. I will explain both using the movement of electrons, as these are always caused by either their rotation or their translation. Let's look at the former. Classical magnetism is caused by the magnetic field induced by the outer electrons of a magnet that are all aligned in the same direction. This field points in one direction, which is usually south to north inside the magnet itself. We will postulate that these electrons merely amplifies the chaotic electromagnetic background that I mentioned earlier, in the same direction as the magnetic field. In fact, this amplification would be the magnetic field itself. Any ferromagnetic material will optimize their outer electrons, which are the electrons that suffered most of the electromagnetic background postulated earlier, to a spin which would mimic the spin of the magnet. This would be a synchronization of sorts, and once synchronized, the repulsion between those objects would be lesser than usual, pushing them together from the outside. The third part of this trilogy will explain further. One might argue that a container empty of any gas would then attract any matter from outside, as the electromagnetic background emanated would be null. Contrary to the magnets, though, there is no mass inside the container that can absorb the electromagnetic pressure from matter behind. The reason why only metals are affected by the attraction of magnets would be that only unstable and outer electrons can be as vulnerable to this pressure, and such electrons are mostly found on outer orbitals of metals. For the attraction of two wires with equal current, the translation of synchronized electrons would once again have lesser effects of mutual electromagnetic repulsion. To the point of view of the average electron, all matter is rapidly moving except for electrons with similar movement, causing an effect similar to kinetic force. Once again, a tube empty of matter will not cause such attraction because it simply carries over the electromagnetic pressure from matter behind it. Not only are there many other cases of attraction through electromagnetism, but also these prior explanations have many flaws. To be honest though, I find the current accepted explanation of two wires with currents attracting or repulsing each other almost as unconvincing. At the end of this video, I will add a possible solution to this problem. The weak force which pushes quarks and baryons does not include any attraction. However, if positive and negative charges are removed from the equation, we can simply merge electromagnetism and the weak force into the electroweak force. To be clear, this unified theory is not my own idea. Many peer-reviewed scientific papers have explored such a theory. The removal of charges, however, makes it a simple classical force. Gravity is a far more complicated force, as it is not a typical force in relativity. The accepted general theory of relativity stipulates that our passage of time is slowly transformed into movement through space. The force of gravity is simply our constant resistance to said movement. There are many other consequences of this theory that have never faltered throughout time. Let's look at gravity through a repulsive but classical point of view. Our knowledge of gravity has recently been set further in stones by the discovery of gravitational waves. The attraction of two merging black holes shifted drastically in mere instants, enough for us to detect the distortions of space. What if these waves of attraction were merely waves of absence of repulsion? If we look at the attraction between the Earth and the Sun, it is intuitive to think that one attracts the other depending on its mass. What if they were both absorbing repulsive waves, and such an absorption causes them to be pushed together? Before getting further into this, we would need a source of these waves. A cheap trick would be to say that the expansion of space would create repulsive waves, which would be akin to vibrations of space itself. Mass and light would then be affected almost equally, and both would absorb a part of those waves. In the perspective of any massive object, these waves would come uniformly around all space. Yet, when we add other masses into this equation, a fraction of these waves would be then absorbed, and so each mass would be intrinsically attracted to every other mass. This postulation would respect the field equations and orbital effects such as precession. To the point of view of any mass, it would be the same as if every other mass emanates waves of gravitational attraction. The drag of the curvature of space-time would then be kept as normal. Instead of the curvature of space-time, however, these repulsive waves would simply bend light at all times. When light would cross near a massive object, one side would push more than the other, and so it can be deflected. If light would move toward or against these differences of spatial vibrations, it will respectively be compressed or stretched. In terms of the fundamental property of light, their wavelengths would change. As for gravitational time dilation, just as the part 1 of this trilogy, we can simply state that the deflection of light and the stretching of light will cause the electromagnetic interactions to instead slow down, as light would require more time or more energy to set atoms in their stable state. This has nonetheless a major flaw, as it would imply that electromagnetic interactions going towards a massive object would be different than any other direction. The strong force can then be ironically unified with gravity, the supposed weakest force. The vibrations of space, when converging into the nuclei of atoms, will show their utmost strength. If the totality of a very small volume of pure repulsive force is absorbed by a proton or even a quark, then a secondary similar particle will be fully pushed from behind as it does not absorb any force in front of it. In fact, a pair of massive particles such as baryons or quarks will be pitted against one another by twice the full force of those waves. Those particles will then be in a stable configuration maintained by both these repulsive waves and the electroweak waves of before. Electrons and other lightweight particles will interact too much with the electroweak force to enter such stable configurations. Although I have tried to show repulsive point of views of all fundamental forces, there is one that might arise if we remove the postulation of charges. Matter and antimatter can collide with one another, and under this theory, electrons and positrons should not come close to one another. This event is, however, well documented. Another well-documented event is the capture of positrons and antiprotons with normal electromagnetic fields. The only way to reconcile all of this under the repulsive theory would be to postulate that matter and antimatter interact with each other through the electroweak force with much less strength. This reduced strength could make electrons and positrons attract through the strong force while being able to capture antimatter with very strong magnetic fields. This will be discussed further in the final part of this trilogy. Now, the entirety of this theory seems somewhat useless as it does not describe any new phenomena. It is only another point of view of already accepted theories. Perhaps even absolutely wrong point of views of already accepted theories. Why would this even matter, and how could it be proven given that all known consequences behave just as normal? The last few chapters of this video are insights on why and how this theory can explain the world in a clearer way. First of all, simulating the orbitals of atoms in a classical point of view has always come short because electrons will definitely merge into their associated nucleus. This is one reason why quantum orbitals and Pauli's exclusion principle is the most accepted explanation of the position of electrons. Although I lack the software to simulate what I want, I'm sure that mimicking the behavior of atoms explained in the Microscopic electromagnetism chapter will show a clear picture of reality. If we simulate the nuclei of atoms without simulating the nucleus-to-nucleus strong force, we will observe a sea of nuclei in a grid formation. If we add electrons which are repulsed by only the protons, while the inverse force would be insignificant, then these electrons will fly off to the corner of the grid. If we can simulate the absorption of electromagnetic waves from nucleus to nucleus, electrons should now stick to their closest nucleus. If we add the electron-to-electron repulsion, each nucleus will have a maximum number of electrons before they would knock each other into other orbitals. If the atom grid is saturated with electrons and we add the dipole moment of electrons and nuclei, then I believe we will naturally end up with a known representation of orbitals, but in a classical point of view instead of a quantum point of view. Now, a second insight would be the stability of nuclei given these repulsive representations of the strong force and the electroweak force. From what is told in this video, the strength of the strong force should come from outside the nucleus and the weak force from inside. Each added baryon should then increase both forces, but in different scales. Let's put together the presumed formula for the stability of the nucleus with X as the number of baryons. We will use already known formulas such as the surface of a sphere, the volume of a sphere, the ratio of proton to baryon, and the ratio of neutrons to baryons. X, the number of baryons, is already representative of an increase of volume, so these formulas will change like so. Let's put them all together to form an intuitive formula. The resulting formula would then have this structure. It is known that neutrons are not electromagnetically interactive, so we must add a coefficient to at least reduce its electroweak strength. If we set an arbitrary coefficient of 0.179, the graph of this formula will look like this. This is not representative of the nuclear binding energy of different elements, yet these 2 points are too coincidental to ignore. Indeed, the atomic mass 58 is nearly the mass of the most stable elements of the periodic table, which are around iron 56. At mass 208, we find the first heavy radioactive element, bismuth. It is almost unnoticeably radioactive, but if the graph truly exposes the stability of nuclei, then being as close as 0 in the y-axis would indeed expose its radioactivity. Seeing the strong force as compressing nuclei, while the weak force as expanding them, could very well explain the overall nuclear stability of different elements. Finally, the third insight would be experimental. The mentioned chaotic electromagnetic background is unseen in our down-to-earth world, but in spaces where density of matter is almost inexistent, this background would be diminished extensively. I am not talking about rooms vacuumed of their air, which are still surrounded by dense material. Around the Earth, where artificial satellites orbit, such is the place which electromagnetic effects would be globally lessened. An experiment that would disprove this theory completely would be to simply put a ferromagnetic object in 0G and then introduce it to a magnet. If there is nothing beyond the ferromagnetic material, then there should be nothing to push it toward the magnet. I find this outcome extremely unintuitive given our knowledge of magnetism, yet this could be a chance to either prove that at least electromagnetism is purely repulsive, or to strengthen our knowledge of magnetic fields. This repulsive theory can also explain an unexplored aspect of physics. The last video of this trilogy conceptualizes the nature of particles and links their usual fundamental properties to intuitive and physical causes.